Logical values. So these notes are designed to follow up on the DataCamp course Intermediate R. And the focus is on logic, but I did include some stuff from other parts. If you want to know about logic or Boolean values, Boolean algebra, there's a good reference here to kind of bring you up to where this stuff came from. And the idea here is really to give you enough experience with logical expressions to distinguish them easily from normal algebraic expressions. The notes are in question and answer format, which means that you really need to be working through them actively. So you should have RStudio open on the same screen where you're going through this. And as questions come up, I'll point to places in the notes where you should stop and do something, and it's really important that you take the advantage to stop and work through the thing in RStudio. Okay? So the first issue is dealing with NA values. Obviously 7 is not NA. Therefore the expression 7 is equal to NA should be false. It's also clear that NA itself is NA, therefore NA is equal to NA should be true. You notice that I just wrote the English word false here and didn't give the correct R typing, which is capitalized. Okay? Anyway, let's try those things. Oh, this is one of those places where you have to stop the video, go over to RStudio, and actually try those two expressions and see what happens. Okay, I assume that you stopped the video, that you went over to RStudio, did your thing, and now you're looking at your results, and here are mine. If I say 7 equal NA, I expected false, and what I got is NA. And I typed NA is equal to NA, and I expected true, and of course what I got is NA. I didn't really expect those. The key expression that we're dealing with here, or the key fact that we're dealing with here, is that anytime you have an expression which involves NA, the result is NA. So how do you ask questions about whether or not something is NA? And there's a built-in function, is.NA, which will do the job. And let's see what happens when we use that function, is.NA, with 7, and do it yourself, and come back, restart the video, okay? Okay, you're back, and here's the answer. If I ask, is 7 NA, is.NA of 7, I get false. And if I ask if NA is NA, I look at is.NA of NA, and I get true. Okay, great. Things are working the way they should. Most presentation of logical operators at the very beginning use truth tables to define precisely what is meant by a logical operator. A truth table always starts out with 2 columns, the possible values of P and the possible values of Q, and then you see added to the truth table, you see the column for the thing that you're looking at, P and Q. So there's a standard pattern which would be generated either by a nested for loop or a tree diagram, in which you first noted that P could be either true or false, and then if P is true, Q could be true or false, and if P is false, Q could be true or false. And those 4 give you these standard base columns, as they call them. So here's the column that literally defines what is meant by P and Q. So you should do the example, follow the example above and construct a truth table for the OR operator, which is written OR in R. And note that in Boolean algebra, OR means the inclusive OR. It's not OR in the sense that you can have the cake or the pie. You can have both. So if both of the operands are true, the result is true. So go ahead, stop the video, do that, construct a truth table for the OR. See what the operator or vertical bar does in R. Okay, I assume you stopped the video and you did your thing. And now you see this. And you see that P or Q is true, 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 false. That is, in the case where both of them are true, P or Q is still true. You can define something called the exclusive OR, in which this row would have a false value. But the normal meaning of OR in Boolean algebra is this column. Okay, then there's NOT. It's very simple because it's a unary operator, so its truth table only needs 2 rows. And you can create this table for yourself. So go ahead and do that. Stop the video, do it, then come back. Okay, you're back. So I created something called P1, so I didn't wipe out the P I'd created earlier. And I created not P1, it's exclamation point P1. And here is the truth table for it. If P1 is true, not P1 is false. If P1 is false, not P1 is true. Logical equivalence. What do you mean the two expressions in logical variables are logically equivalent? What you mean is that for every possible value of whatever the variables are, the two expressions give the same truth value, true or false. And here's one of the standard examples you'll always see at the beginning of this kind of material in any textbook. I have expression 1, which is not P and Q, and expression 2, which is not P or not Q. It comes as a surprise to some people that the and here kind of became an or here. So we can decide whether or not these two things are true by building a truth table which contains both of these columns and see if they give you the same thing. So again, as usual, I want you to stop the video and go do this in RStudio before you look at what I did, and then come back. Okay, you're back. I assume you did your thing over in RStudio. Let's look at what I did. Here's the P and the Q. And here's expression 1, not P and Q. Here's expression 2, not P or not Q. And then I put them together, and all those 4 things together into a data frame, and print out the data frame. And I look at the 2 columns for expression 1 and expression 2, and I see that in every row they have exactly the same value. Okay? Did we need to look? Could we just compare the 2 logical vectors? Well, yeah, we could. Exercise, do that. Of course, whenever I say do that, that's also your cue to turn off the recording, to pause it for a minute, and go do something, and come back after you've done that, okay? Okay, you're back. I assume you've done that. So let's go look. And it's real simple. I ask, is expression 1 equal to expression 2? And what I get is that this logical expression gives me a resulting logical vector, and the values of that resulting logical vector are printed out here, and they are all true. So I still had to look. It was real easy to look, true, 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 true. No problem looking at it, but maybe you'd be dealing with someday a really great big long logical expression, and you'd want to not have to look at each one individually. How could you simplify the conclusion? Well, the idea is that we want to see if the count of true values in the logical vectors is the same as its length. Exercise, do that. And remember that to get a count of true values, what you do is take the sum of the logical expression. So stop the video, go do it, then come back. Okay, you're back. And I calculated the sum of the logical expression, and it says there were 4 truth values in that sum, and I calculated the length of the logical vector, and it's also 4. So they are the same, so it's not possible that there were any false values because they were all true. And, well, okay, so I'm going overboard. I could ask the question even more directly. How could I do that? The way is obvious. You say, is this equal to this? Okay, do that. Pause the video as usual, go do it, and come back. You're back. I assume you paused the video and you did it, so let's look. So I ask, is this sum equal to the length of this thing? And this time there is only one true value because the whole thing is true. And that particular logical equivalence is one of De Morgan's 2 laws. And the second one is almost the same, but the 2 logical operators are reversed in their roles. And you can imagine what that looks like, and if you're curious, you might want to build a truth table for it and see if it's true. It's also good to think about in English why it would be true. Another law we have from normal numerical algebra, if you have any 3 numbers, x, y, and z, x times y plus z is x times y plus x times z. And I know you did this exercise many times in factoring polynomials and things like that. And there are 2 similar laws in Boolean algebra. We'll just look at one of them. There's only one in numerical algebra, but there are 2 in Boolean algebra. So the distributive law, one of the 2, is that P and Q or R is the same as P and Q or P and R. And this time we got 3 logical variables, P, Q, and R. Remember, the truth table with just 2 base logical variables, P and Q, had 4 rows. Now, when you introduce a 3rd logical variable, each of those 4 rows branches into 2 rows because whatever the values of P and Q, there are 2 possible values of R. Okay? So maybe I don't want to do a truth table. But computing the values of the 2 logical expressions for every possible, misspelling, for every possible combination of P, Q, and R would be easy using nested for loops. Yeah, I told you there'd be something in here besides logic. So nested for loops. Yeah, you can do that, can't you? Go ahead, do that. Pause the video, do that, and come back and look at my solution. So here's my solution. I created a vector called TV, an abbreviation for truth values. It's T and F. So for every possible P in TV, for Q in TV, for R in TV, and you see how this pattern of nesting generates the truth table. I create a simple value. exp1 is P and Q or R, and expression 2 is P and Q or P and R, and I print just the simple value. This is only a 1 long vector. exp1 is equal to exp2, and I see that in every case I get true. So that's a not R-ish, very R-ish way to do things. People who've gotten used to R tend to do everything with vectors and avoid for loops. And you could generate the base columns of the 8-row truth table as follows. This is simple brute strength. TTTT, FFFF, TFTF, TFTF, TF, TF, TF. Those are the base columns. And I'll just create the base columns data.frame P, Q, R. Then we can create the expressions we want using vector operations and test the equality of the 2. So expression 1, expression 2, And I ask, is expression 1 equal to expression true? And I see 8 possible values, and I'm not going to go back and do what I did before. You can just look at the 8 possible values and see all of them are true. If you're kind of thinking about this excessively rote, brutish way of building P, Q, and R, and you want to do something more sophisticated, you could use the repeat function, REP. And there's a good explanation of it at this site. If you go read that and figure out how rep works, then you could use it to build P, Q, and R. And after you've done that, come back and look at mine. Okay, so now go, of course, go stop, read the material that I pointed out to you, and come back and do it. And then after you've done that, look at my solution. Okay, stop the video. Go do your thing. Okay, you're back. Let's look at the way I did it. So to create P, you repeat the vector t comma f, and each is 4. That gives me 4 of each, 4 t's, 4 f's. Then for Q, I just repeat TT, FF 2 times. Notice how instead of specifying the parameter each, I specified the parameter times. And then to create R, I take the vector TF and I repeat it 4 times. And that gives me my standard display. Okay, so that's the end of the notes on logical things.